So the time is now 4 p.m., so I'm going to go ahead and get started. And as you probably heard, I've already begun the recording of this webinar, so it will be available for you to view later on our YouTube channel. So hello and welcome everyone, and thank you for joining us today. My name is Brooke McDonald. I'm the Education and Outreach Coordinator for the Blue Hill Heritage Trust. And before I introduce our presenter today, I'm going to go over just a couple housekeeping items, like how to use certain Zoom functions and what to expect with the Q&A session of this program. So if you have any questions during the program, go ahead and put them in the chat. There is a little chat icon located at the bottom of your screen. You might need to hover your mouse over it, and that'll come up. Once you select it, you can see that you can have a message to either the hosts and the panelists or to everyone. So you can go ahead and select, and then just put your question in there. We will have time at the end for answering questions. It is a large group. We are expecting a big group today, which is awesome, but we might not be able to get to everything. But we'll talk to you about how we can answer questions that we haven't gotten to by emailing us at the end of the session. So there's also a little closed caption icon at the bottom. So if you hover over that and select it, you'll get closed captioning. Today's talk is titled Tremendous Tides in the Gulf of Maine. The Bay of Fundy and the Gulf of Maine are home to some of the most extreme tides in the world. So to teach us more about that is one of our wonderful interns that we've had with us all summer, Vienna Melzel. Vienna is one of 3 interns who've been with us doing a lot of different things, but you've probably seen her out on the trails. She's been helping our trail stewards and all of our land team and everybody in the office. So we've been really, really fortunate to have 3 fabulous interns in Vienna's presentation. We're really looking forward to it. She is a rising senior at the University of Maine, Orono, where she studies environmental science and marine science. She's taken oceanography classes as part of the marine science program, and she's really excited to share some of her knowledge today with all of us. So without further ado, I'm going to turn it over to Vienna.
Hi, everyone. So like Brooke was saying, my name is Vienna Melzel, and I am one of the 3 summer interns here at Blue Hill Heritage Trust. So we're just going to start off by telling you a little bit about me. So I attend the University of Maine studying ecology and environmental sciences and marine sciences, but I actually grew up in Wisconsin. And my first summer after my first year of undergraduate, I worked with the Wisconsin Department of Natural Resources in a state park. So working here at the Trust has been a really cool way to kind of see a different perspective on land conservation and land management. And I've been in Orono for the past 3 years, but Maine, being here on the coast, is like a completely different state than Maine that I see when I'm in Orono. So it's been a really fun summer and I'm learning a lot, and it's been super great to be in this community in this area. So let's get into it and start talking about the tides. So first of all, what are the tides? If you guys are from this area, I'm going to assume you have at least kind of a baseline knowledge of the tide is when the water is higher and then it's lower. So this is actually the tide chart for today. This is from United States Harbors. They have the tide charts, and you can download actually like the monthly tide breakdowns. So you can see based on this graph that the tide was high just after 8, and then it was low kind of right at 3 p.m. and then it'll be high again kind of towards 9 p.m. So to give some more technical definitions to that, a tide is actually a large scale wave that the water moves through, and the crest of that wave is what we experience as high tide, and then the trough is what we experience as low tide. And you can see that really well on the tide chart because it does show you kind of the sine curve that it creates. So that's pretty cool. And then the actual tidal range is what we mean when we refer to the difference between the high and low tides. So on this chart, you can see in Blue Hill, the tidal range is about, today at maximum, it's about 9 meters because you have a high tide up here at about, 9 feet. You have a high tide up here at about 10 feet, and then the low tide is down here closer to 1 foot. So that tidal range is about 9 feet, and that varies actually depending where you are on the coast. But that's what it is for here in Blue Hill Harbor. So talking about why we have the tides, we can't have this discussion without first bringing up gravity. Gravity plays a huge role in multiple different ways. So I'm assuming you guys know what gravity is, just kind of what keeps your feet planted on the earth. But the gravity that we're going to talk about when we talk about the tides is a little bit more complicated than that. So we're just going to take a little side detour and explain that a little bit more just to make sure we're all on the same page and have the same information that is going to build with everything else. So according to Sir Isaac Newton, every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers of mass. That's a pretty dense definition. We don't need to understand gravity on that level to make sense of the tides. So the main takeaways that I want you guys to keep in mind moving forward is just that anything that has mass has gravity. So yes, the Earth has gravity. That's why our feet stay on the ground. But I have gravity. My computer has gravity. You guys all have gravity. But the reason we don't notice everything getting stuck together and attracting each other is because more mass means that you have a stronger gravitational pull. So in terms of the Earth compared to my gravitational force, the Earth is going to be way stronger than mine because I have much less mass than planet Earth. And then finally, the closer together two objects are, the stronger their gravitational pull will be. So again, that kind of comes into play when you think about the moon and Earth, they stick together, and then obviously the Earth is still attracted to the sun. And the difference between the mass and the proximity relationships is that more mass will create a stronger gravitational pull in a linear association because that is a proportional relationship versus the proximity. If you move two objects closer together, you will exponentially increase their gravitational attraction to each other. So those are the things that we need to keep in mind when talking about the tides to make sense of those. So there's actually multiple different kinds of tides. We know that the sun has gravity because that's why the Earth orbits the sun. And that gravitational force actually shows up in the tides. A diurnal tide is a tide that's controlled by the sun's gravity. And a diurnal tide, you can see on this little chart, is when you just have one high tide and one low tide every day. That's not what we have here in Blue Hill. We actually have semi-diurnal tides, which are dominated by the moon's gravitational force. And we'll explain how that works and why there's a difference between these two, but you can see in the chart, the most obvious difference is that a semi-diurnal tide has two high tides and two low tides every day. And there is a third kind of tide, and that would be the mixed tide. They call it mixed semi-diurnal because there are two high tides and two low tides every day still, but they're mixed because the sun's gravitational force interferes and it makes one of those high tides and one of those low tides more extreme. So there's still two high tides, two low tides, but they're not equal and they're not as close together. There can still be some variation in semi-diurnal, but mixed semi-diurnal, it's very, very clear that there's something else going on there. So this map shows you the breakdown of the kind of tides that different coastlines experience. So you can see Maine up here is semi-diurnal, and then you have diurnal in other areas, and then other areas still have the mixed semi-diurnal. And the reason why we don't just have all mixed tides, as you would think, because everyone's kind of experiencing the same attraction of the moon and the sun, because we're all on the same planet, we're all in the same proximity to those two celestial bodies, is just due to the ocean floor and the geography of the coastline. The kind of bathymetry, which is what you call like how the ocean floor is laid out, the topography of the bottom of the ocean, those kind of interplay with the actual tidal forces, and that interferes with the kind of tides that you experience. So you could definitely find a much more detailed explanation for that somewhere, but that's all that I can give you because it gets pretty complicated. But yeah, it's kind of cool to see that different coastlines have different tides, even beyond just the tidal range. It's actually the pattern itself is different. So moving on to discuss more semi-diurnal tides, we're going to focus on those first since they're a little bit more complicated, and those are what we experience in Blue Hill, so it's a little bit more close to home. To explain those, we're again circling back to gravity. So when we're talking about the Earth and the Moon system, a lot of times we just kind of portray that as a stationary Earth that has the moon orbiting around it. But that's actually not the case. Since the Earth and the moon both have mass, they both have gravity. So because of that, the moon is pulling on Earth just in the same way that the Earth is pulling on the moon. And the result of that is they both orbit around a point, which is called the barycenter, and that is their common center of mass. And that's because at that point, the gravitational pull of the moon on Earth and the gravitational pull of the Earth on the moon are equal. So it cancels out, and that is the point that they orbit around, and we don't actually get pulled together. And if that point was the center of the Earth, then it would be the case where we just have the Earth and then the moon is orbiting around it in that kind of the way that you'd see in a model solar system. But that point is not in the center of the Earth. It's actually about 3,000 miles outside of the center of the Earth. And that's because, again, the mass of the moon and the gravitational force of the moon pulls that point away and shifts it. So since it's 3,000 miles away from the center of the Earth, that results in the Earth kind of moving in little circles as it orbits the sun. And then the moon is still spinning around the Earth. That is true, just not quite as simple as we kind of make it out to be sometimes. And I know this is confusing, so this is a visual. This graphic kind of shows how the Earth is spinning in circles on that green track, while the moon is spinning around the Earth, yes, but also around that barycenter, which would be this point right here. And that's how that system is acting as a whole. And then collectively, those both orbit the sun. And there's a lot of moving parts. But as you can see, since the Earth is spinning in that little circle, that's going to generate centrifugal force that's directed away from the moon. So if you guys have ever been on a merry-go-round and you spin it really, really fast, and then you feel yourself start to get pulled to the edge and you kind of have to hold on or you're going to get thrown off into the wood chips, that's the same thing that's happening here, just on a way bigger scale. As the Earth spins around, it generates that force pointing away from the moon. So to recap the different forces that we have at play so far, we have the centrifugal force pulling away from the moon. So as the Earth moves in this circle, you have these force arrows, and they just point opposite of the moon. And since the moon is spinning and everything's moving, it's not just one set direction, but it is always pointing directly away from the moon. But at the same time, you have the gravitational force of the moon that's pulling towards the moon. So that gravitational force and that pull is actually the same mechanism that comes into play during diurnal tides, except in that situation, since it's ruled by the sun, you're just kind of focusing on the gravitational pull of the sun towards the sun. So we'll circle back around to that. But that's what's happening with diurnal tides. The difference is that with semi-diurnal tides, you also have that centrifugal force that's pulling away. So this diagram kind of shows it better than I'm probably explaining with my words, but you have the centrifugal force pulling opposite of the moon and the gravity of the moon pulling towards the moon. And then that acts on water to create these two tidal bulges on opposite sides of the Earth. And those are what we have as high tides in a semi-diurnal tidal scheme. And then the Earth itself rotates and it goes underneath those two tidal bulges. And since the Earth rotates once every 24 hours, that's what a day is, we experience 2 high tides and 2 low tides every day. So the difference is that the semi-diurnal tidal period is about 12.41 hours versus a day is 24 hours, half a day is 12 hours. And that difference there, that extra 0.41 hours, is why we don't have tides at the same time every day. That's why we need to have tidal charts like the ones from US harbors, because it does shift and it gets later each day, or yeah, it shifts later each day because of that extra 0.41 hours. It doesn't line up perfectly with what we experience as a day. And so that's why it kind of changes each day, if you'll notice that. And then thinking about tides around the world, just in terms of their range, you can see that the pockets of red are the most extreme. This data set had a maximum of about 13.5 meters is the unit for this. But tides can actually be as extreme as 15 meters. But you can see there's a wide variation in the range that different areas experience. So the center of the ocean doesn't have a whole lot of change in sea level during the tides, which kind of makes sense because it's not really moving in around. And then you have the coastlines where you do kind of get the more extreme pockets, and then everything else kind of settles around in the middle ground. Zooming in a little bit, this is the Gulf of Maine. Blue Hill is right kind of in this area. The scale is kind of hard to tell because it doesn't have a great labeling system, but the tidal range in Blue Hill is about like 3 to 3.5 meters. It does vary a little bit because the tide isn't the same every single day, and we'll talk about that in a little bit as well. But you can see up here, this is the Bay of Fundy, and this area is called the Minas Passage. Those are where the most extreme tides in the world happen, and you can see how it gets more and more intense as you move up into those areas. Zooming in even more, this is the Bay of Fundy. This is the Gulf of Maine. This pin right here is the location of Burnt Coat Head Park. And I'm showing you this to just give you some geographical context for the video that we're going to play. So this just shows it's a time lapse of the tides. These are really extreme tides. So I'm going to play that. You can see just how intense they are. And also keep an eye on the timestamps, because you can see that it kind of starts with the first low tide around 9 a.m. And then the tide comes in. And then that's high tide with 50 feet. And then it starts going back out. And then it hits the second low tide right around 9 p.m. So that kind of shows you the semi-diurnal tidal period of about 12 hours. It had that first low tide, and then it has the second low tide roughly 12 hours later. But the main thing I wanted you guys to see is just how crazy the tides can get. They're pretty significant in Blue Hill and in the Gulf of Maine, but the Bay of Fundy is where they are the most intense. So that's just kind of a visual of how intense they can get. It's pretty cool. And then we can get to transition. Yep. So this graphic, it shows the current speed and direction, current as in the water current, not like the current speed right now, during the flood tide on this graph to the left. And the flood tide is when the water is flowing in. So this is when the high tide rolls in. And then it shows that same measure, current speed and direction during the ebb tide on the right. And that is when the water is flowing out. So that's when you're getting into your low tide. And you can see during the flood tide, you get higher speeds, and it gets up to 3.5 meters per second, which, to put that in a little bit more of a familiar unit, that's about 7.8 miles per hour, which doesn't sound like that fast when you compare it to how fast a car can drive. But if you think about that amount of water moving at that speed, almost 8 miles per hour, that's a lot of movement. That's a lot of energy. It's pretty impressive. And then the speeds aren't quite as intense during the ebb tide, but still they're kind of around in that 2 to 3 meter per second range. So then that kind of begs the question, why are the tides so intense in the Gulf of Maine and in the Bay of Fundy area? And that's what we're going to get into next. The main thing is the basin shape. So the actual shape of the Gulf of Maine and heading up into the Bay of Fundy, that actual geography of the coastline has a lot to do with why they're so intense. And there's a couple ways that it kind of carries over into the tides. But to explain that, we need to take another little side detour and talk about the Coriolis effect. So the Coriolis effect describes motion on a rotating sphere. The first time that I learned about this, it took me a second. It took me a second to actually wrap my head around it. So if this isn't making sense, don't worry. The main things I just want you to understand is that objects in the northern hemisphere, when they're moving through a fluid, so like water or air, they're going to shift off to the right of their original course. And then objects in the southern hemisphere are going to shift off to the left of their original course. And this is all because the Earth rotates counterclockwise, and that has an impact on that motion. So this graphic kind of shows it a little bit more visually. So you have a starting direction heading north in the northern hemisphere. Your course will divert off to the right, and you'll end up heading kind of more east than you would have planned. And then if you were heading south in the northern hemisphere, you're still going to adjust your course to the right and end up heading slightly more west than you would have planned. And that holds true no matter what distance you start traveling in. You're always going to kind of diverge off slightly to the right in the northern hemisphere and slightly to the left in the southern hemisphere. And this video shows a bit more motion of how that looks. So you have the starting point and the intended path, and you start off on that path, but then as the Earth rotates, you end up not traveling exactly there. So I'm going to play that again because it's a little quick, but that is the best kind of visual illustration I can show you guys to kind of show that effect in action. And again, you have this is in the northern hemisphere, so you kind of are going off to the right as compared to where you started traveling, it goes off to the right. And if it was in the southern hemisphere, again, it would be the opposite. You would go off to the left. So when we apply that to the tides that we experience here in the northern hemisphere, that just means that the trajectory of the water that moves into the Gulf of Maine is going to curl off to the right a little bit. So due to the Coriolis effect on the water's movement and the shape of the Gulf of Maine, we experience something called tidal sweeping. And that is basically where the water is moving into the Gulf of Maine, but due to the Coriolis effect, it gets kind of swept off to the right, and then it heads up into the Bay of Fundy, and the water movement is kind of concentrated on that side of the Gulf. And so a very high volume of water ends up being funneled into the Bay of Fundy. And you can kind of see how that manifests itself in the tides. Because if you think about it, if you have all that water being moved into a smaller space, you're going to have a higher tidal range because that water is still moving and it just has less places to go. So then you experience a higher change in the tides. If you think about a garden hose, when you have the water just running out normally and you stick your finger over it, you have the same volume of water, but now it has a smaller area to travel through. So it ends up coming through at a higher pressure and it's more intense and the water kind of will spray farther. That's the same idea as with the Bay of Fundy constricting that water flow. As you move up into these more narrow passages, it's like you're putting more and more of your thumb over that garden hose. So you're going to get a higher and higher high tide rise, and then you have a higher tidal range. So you can see that really prettily here with the ombre of the scale. And then you can also see it here. This is just the Bay of Fundy, but it shows numerically the actual tidal ranges. And then all the way up here in the minus passage, you can see those almost 50-foot tides like we saw in the video from Burnt Coat Head Park. So, and that also explains why when we were looking at the current speed and direction during the flood tide, we had those higher speeds of about 3.5 meters per second because the water is being constricted. It's flowing into that Bay of Fundy and you have the same volume, but just a much smaller way for it to pass through. So you're going to have those higher speeds and higher tidal ranges. But when it's flowing the opposite way, it's flowing from the more constricted area out into the open ocean where it has way more space to expand. So you don't have that same constricting effect. So that's like if you took your thumb completely off of the garden hose and the water just can flow out normally, you don't have that same impact. So that's why the speeds are not quite as high during the ebb tide. So the basin shape has the impact through the tidal sweeping and the funneling. Those two kind of work together like we just talked about. And then there's also positive interference that happens, and that actually amplifies the tides even more. So like we said before, the semi-diurnal tidal period is about 12.41 hours. And that's important because the Gulf of Maine's natural period of oscillation is about 12 to 13 hours. So those numbers are very close together. And what I mean when I say natural period of oscillation is that is just the time that it would take the water in the Gulf of Maine to naturally go from one side to the other and back. One oscillation would be a wave like moving all the way through the Gulf of Maine and moving all the way back. So I have this little video. Imagine that this Tupperware is the Gulf of Maine and the water inside is the ocean. If you started a wave off, the natural period of oscillation is the time it takes for that water to get from one side to the other and back. That's the natural period of oscillation. So Since those two numbers, the semidiurnal tidal period and the natural period of oscillation, are so close together, they kind of reinforce each other and they create resonance. So I'm going to play this video, which shows a similar concept. Obviously, this is very abstract compared to an actual basin of ocean water and the tides, but you can see the liquid inside is sloshing, and then the box around it is actually moving as well. And it's moving in resonance with the wave motion inside the container, and that is amplifying the wave motion. So you can see as it goes on, the wave gets higher and higher, and that motion gets more and more amplified. So this is similar conceptually to what's happening in the Gulf of Maine during the tides. The water itself is just naturally kind of sloshing back and forth at that natural period of oscillation, that 12 to 13 hour range. And then the tides are coming in and out kind of in tandem with that natural oscillation. So that results in, like, the motion of the box is kind of the way the tides act. They reinforce the movement, and then it creates resonance, and that ends up amplifying the tides even more than they already are. So you can see, just as that motion continues, the liquid gets higher and higher, and that wave gets more and more amplified, and the motion gets more extreme. So that's a cool abstraction. It's kind of difficult to see the carryover to the actual Gulf of Maine since it's very different. It's a much larger scale, and it's much less perfect and contained than that, but that kind of shows the idea of resonance that's coming into effect. So like we said, that creates resonance and amplifies the tides even more. And that is the way that the basin shape impacts the tides. And like I said, that's the main driver, but there are some other kinds of interference that also work with the tides. And that's the idea of spring and neap tides. These might be a bit more familiar terms, but spring and neap tides result from the interference between the diurnal and semidiurnal tidal components. So like we were saying, there's the diurnal tidal bulge, and then also the semidiurnal tidal bulges, and the interplay between them is what results in the spring and neap tides. And when I said that the tidal range in Blue Hill is between 9 and 11 feet, but it's not always the same, that is also because of the spring and neap tides. So the mechanics of this one are similar. You have your semidiurnal, two tidal bulges, and then the sun, you have your single high tide bulge pointing toward the sun. And during the spring tide, that is the strongest tide. So that here in the Gulf, or here in Blue Hill, we're all in the Gulf of Maine, but in Blue Hill specifically, the strongest tide that we experience here is a little over 11 feet. So that is going to be during the spring tide. And that is when the Earth, the sun, and the moon are all aligned. So that means that the solar tide, this diurnal tidal bulge, which is the orange one, and then the semidiurnal tidal bulges are lined up. So that kind of means that as you rotate under that, you have the force of both the sun and the moon pulling directly in the same direction. So since that is a larger force, the water is kind of raised even more. So you experience that higher high tide. And the sun, the moon, and the earth are aligned during the new moon and the full moon. So that's when you'll experience the spring tides. And on the other hand of the equation, you have the neap tides, which are the weakest tides. So for us in Blue Hill, that's going to be about 9 feet, give or take. And that is when the sun and the moon are at right angles, because that is the maximum where the sun's pull and the moon's pull are going to be as most opposing. There's the different components of the force. Obviously, they're kind of pointing perpendicular to each other, but that is when they kind of negate each other the most. So that is when you have the weakest tide. And that happens at the first quarter moon and the third quarter moon, if you're familiar with the lunar cycle. And so overall, the strongest tides in the world are in the minus basin because of that tidal sweeping and the funneling and the interference during a full or new moon, because those would be the spring tides. So that's when you could find the highest tides in the world anywhere globally, which is pretty cool because it's not quite the Gulf of Maine because that's up in the Bay of Fundy, but it's still pretty close to home. And yeah, the Gulf of Maine still experiences all of these. I know we focused a lot on the Bay of Fundy since it is just the place where there's the most extreme tides in the world, but these same concepts apply to why the Gulf of Maine has the tides that we do. They're not quite as extreme, but they are significantly on the higher side, which is pretty cool. So as you can imagine, there's a lot of energy associated with the tides moving in and out, especially at the speeds that they are up in the Bay of Fundy and even in the Gulf of Maine. So that brings me to the idea of tidal power potential. So all that water movement, you can derive energy from it in a couple different ways. There's the potential energy, which refers to the tidal range, just the way that high tide is at a different height than low tide. There's potential energy associated with that. And then there's also just the kinetic energy of the actual water flowing in and out as you experience high and low tides. So the Bay of Fundy has a theoretical maximum output of 7.1 gigawatts. That's a unit of electricity in terms of tidal power. So in theory, the most power that you could generate from the tides in the Bay of Fundy would be 7.1 gigawatts. And that estimate is from a study by Pelling and Green in 2013. I know that is a slightly old paper, but the other ones I saw had similar estimates around that 7 to 8 gigawatt range. So that's just the one that I went with, but there is other literature on that subject if you guys are interested. So don't take that as the end all be all, but that's obviously the theoretical estimate, but that's kind of where the numbers tend to hover around. And just to put that into context, Vineyard 1 offshore wind, which is off the coast of Massachusetts, that's the first commercial scale offshore wind facility that the US has kind of taken on. That one's output is 800 megawatts. So that's just not even on the same scale as the potential output of the Bay of Fundy. 7.1 gigawatts and 800 megawatts, you have a whole order of magnitude difference between those. So it's a very significant amount of energy that could be derived just from the Bay of Fundy alone, let alone even the Gulf of Maine. So it's just cool to think about how much power is going on in there. And then in terms of tidal power, it's not something that's new. I honestly hadn't heard about it a whole lot, but the Annapolis Tidal Station, which is up in the Bay of Fundy, so it's a Canadian facility, but it actually first opened in 1984, and it operated all the way until 2019 when it was closed after some parts failed. I'm not sure exactly what the rationale was, but I'm assuming parts failed, and then it just wasn't worth it to maintain it and open it back up. But that had an output of 20 megawatts. So obviously much smaller scale, even than offshore wind is at these days, and much smaller scale than the total capacity of the Bay of Fundy. But it's not a new idea. It has been around since the 80s, and it's still being developed. There's an organization called the Fundy Ocean Research Center for Energy. Their acronym is FORCE. And they actually have an ocean test site in the Bay of Fundy where they've been developing different types of tidal power technologies, which is pretty cool. So this is technology that's been around and it's still being developed, and there's a lot of potential with it, especially since there is so much power that can be generated even just from the Bay of Fundy alone, let alone the Gulf of Maine or the oceans as a whole. There's a lot of water moving in a lot of places around the world. And one thing about tidal power is it's kind of attractive as a clean energy solution because it's not only renewable, but it's also reliable. So the movement of the water, like we talked about, is based on the gravitational pull of the moon and the sun, which isn't something that human activities can really alter at all. That's a whole different, like, astrophysics. We're not going to stop orbiting the sun anytime soon. So that's a pretty safe bet. We can rely on that. And then the tides happen. We aren't planning on those going away. Sea level rise will alter how the tides happen a little bit, but the movement of the water is kind of set in stone. And when you compare that to other kinds of renewable energies like solar and wind, those are renewable, but they are not as reliable since they are dependent on the weather. If you have a cloudy day, you can't generate as much power. If you don't have the wind, you can't generate as much power for those respective kinds of energy. So that's kind of why it's a really cool idea to think about, especially since it doesn't have as much exposure. But like I said, the technology has been around and it's still being developed today. So we're just going to talk about that a little bit more since I think it's really interesting. There's 3 different types of tidal power generation. The first one is barrages, and then there's tidal lagoons, and there's in-stream devices. So we're just going to go through and kind of break these down one by one so you guys can understand the different mechanics and technology that goes into it. So barrages, they harness potential energy. So they work with the difference between high tide and low tide, which is why the Bay of Fundy is so attractive since they have such extreme tidal ranges in that area. And its design is kind of dam-like, and it's attractive as an option because it does offer the highest output of energy. However, there are a lot of concerns with tidal barrages, mostly in that they're very costly and they also have a lot of impact on the environment. There's a lot of sediment and erosion implications, and there's also a lot of fish mortality associated with these. And I will show you a diagram that kind of explains how this happens, but there actually were two cases of humpback whales. One of them was trapped upstream of the Annapolis facility, which is a tidal barrage device, and another humpback whale was actually killed at that facility, which I'm sure were also factors in why they decided not to reopen in 2019. But as you can see, this is the location of that Annapolis facility, and this is a picture of what it looks like. But they work like a dam in that they actually just block off an entire kind of inlet from the ocean, and then the water has to go through the facility and spin the turbines for the energy to be generated. So you have the high tide, and then you open the gates, and the water flows back out to the ocean, spins the turbine, and generates energy. And then once high tide comes back, then you would close the gates, let the ocean go back to low tide, and then open them and repeat that process. But as you can imagine, that's severely altering the natural flow of the tides, which is why it has an impact on the sediments and the intertidal zone especially. You're kind of disrupting the natural tidal pattern because you're releasing the high tide all at once. It's not flowing out slowly, so that's a lot more violent motion than the sediment is used to. That's going to stir things up. That's going to alter the bathymetry of the floor, and it's also going to change how long the intertidal zone is actually submerged, which has implications for everything that lives in the intertidal zone. And obviously, in terms of fish mortality, if you have this entire outlet blocked off, the fish, unless you have a fish fridge or anything, but I don't think they had applied that technology to this facility in that time. So that's why there's a lot of issues associated with this. And in terms of cost, you can imagine how expensive it is to kind of block off an entire area from the ocean. So those are tidal barrages. Moving on to tidal lagoons, these also work with potential energy, and they're similar to the barrages in that they are dam-like, but they are actually a self-contained structure, which slightly lowers the cost and the impact because it's not just blocking off an entire outlet, it's just kind of taking a single area and containing it. And these can actually generate continuously, which is a plus. The output for barrages is still higher because you have a larger scale with it, but there are the same concerns as with barrages because it's kind of the same concept, just on a smaller scale. So still not perfect, but this is what I mean when I say that it's self-contained. You actually just kind of wall off an area of the coast, and then when the sea is at high tide, you open the gates and let the water flow in. Then you can close them, and then when the sea is back at low tide and you have the high tide level inside the lagoon, you can open the gates again and still generate energy from the water flowing out. This diagram is actually from the Swansea Bay project in the UK. This was proposed back in the 2000s, and they had secured funding for it, but then the government pulled some funding just because they didn't think the project was as feasible as other projects that they could fund. And since then, the project idea has still been kind of floating around and bouncing around, and they're still just trying to figure out the funding for it. But you can see they just kind of have the flow gates here, and then they have the tidal lagoon. And this project I thought was interesting because they had plans for this lagoon to actually be a recreational area. They had areas for like water recreation, like paddleboarding, kayaking, and they also had, I believe it was like kind of a boardwalk built out into the lagoon, which is kind of a nice multi-use solution to generate energy and then also still be using this area for recreation. But as you can imagine, you still are disrupting the natural tidal flow within the lagoon. So you're still going to have those same impacts on the sediments and intertidal zone, and any sea creatures that actually live inside the lagoon or find themselves at the gate can still obviously be harmed by that. So not without its issues, but less extreme than the barrages. It is interesting though, there are other tidal barrages that are still in operation. There's some in Japan and in the England or Europe area. They do have some that are active. The Annapolis one was the only one in North America that really stood out to me, at least on the East Coast. But there are ones that are still operating in different areas of the world, which I think is interesting because that's both like the highest cost and it has the most impacts. But I think that was just the first technology that was developed. So finally, we have the in-stream devices. So these are different because they actually work to harness the kinetic energy. So they're not working with the difference between high tide and low tide. They're actually working with the flow of the water in and out as the high and low tides come. So the way that's done is through a tidal current turbine. So these ones are removable and scalable because the turbines, you can add more or you can take them out more easily than you can construct and build onto a lagoon. With the barrages, it's a limited scale. If you don't have the entire area blocked off, you're not going to generate as much power and you can't expand beyond that unless you're going to severely alter the landscape. So these ones are more accessible, and there's also a lower cost with that since you can do it incrementally. You don't have to commit to the full project right off the bat. And there are also lesser ecological impacts because they aren't blocking off an area, so you're not impacting the sediment as much. You're not interfering with the tidal flow since you're using the movement of the tidal flow. So the intertidal zone is still going to have its natural ebb and flood of the tides. But there are still some concerns, mostly rooted in the fact that there's still limited research on how this technology does impact wildlife. This is the newest of these technologies, so there's a lot of research that's still being done. But this is an image from the FORCE, the Fundy Ocean Research Center for Energy. They have a really cool website. They have a whole learning center. I'm going to send the link to Brooke. I don't think I have access to the whole chat for everyone, but I will send that to her and then maybe she can throw that in the chat if everyone else is interested and wants to check it out. They have a 3D tour of their ocean test site, which is where I got these images from. It's cool. You can spin like all around. You can see the different technologies that they have tested and you can go underwater and see that. So it's cool. I recommend checking it out. And they have a lot of other information about how their monitoring works and the projects that they're working on. So in this picture, you can see these are some of the surface level tidal current turbines. The water speed is highest at the surface, so these would generate the most out of these two different technologies. And here are some of the bottom mounted turbines. Obviously, these ones, just from an outside perspective, kind of seem a bit more invasive to me since you are mounting it on the bottom. That's more labor intensive too, I would assume, since you have to get it all the way down to the bottom and mount it. And I didn't dig deep enough to actually explain the technologies behind these, but if you're interested, I definitely recommend going to that site and checking it out some more. But that just kind of shows two of the different concepts that they've been testing to develop. And they actually do have a pretty intensive monitoring program. They have reports that they've put out, like I think it's annually. But they're monitoring specifically for the impacts that these in-stream devices have on the energy of like the water flow, and then the bathymetry, ocean noise, and then impacts on wildlife. So those are the areas that are still being kind of addressed as this technology is developed. So hopefully we learn a bit more about the impact that these would have, because it definitely wouldn't be smart to deploy them on an industrial scale without fully understanding the impact that they have. But that's where the technology is at now. So it's something cool to keep an eye out for, since I feel like there is a lot of potential, and I think it will be something that grows in popularity moving forward. But to wrap it up, I'm just going to bring it back a little closer to home, and we're going to talk about Blue Hill Falls. So you can see on the map, Blue Hill Falls are right over here. They're just kind of outside of downtown. If you guys are in the area and like are based here, I'm sure you've driven past them or heard of them. If you haven't, though, I recommend going to check them out. The location pops up in Google Maps if you put it in. It's really cool. Go at high tide or low tide. And the reason you want to go at high tide or low tide is because these are actually reversing falls. So there are 8 different reversing falls in Maine. Another one of them is on the Bagaduce. But they're kind of a unique thing to the state of Maine, at least in New England. You can't find them anywhere else. But they result from the constricted flow of the tides. So similar to how we were talking about with the Bay of Fundy, All that water is flowing in, and then once you constrict the space it's flowing into, the water kind of speeds up a lot. It's a lot more violent. So you get these really cool patterns. And in the case of Blue Hill Falls, you have the water from Blue Hill Bay flowing into the salt pond. You can see on the map here how that opening gets much more narrow. So that creates a standing wave, basically. It can get pretty tall. People actually go surf on it. One time I saw guys like holding onto a rope on the bridge and surfing on the wave. I wouldn't do that. It looked really scary, but it's pretty cool. So I'm just going to play this video, and it's a really good example of close to home just how much power the tides have. I know we talked a lot about the Bay of Fundy, but the Gulf of Maine itself still has so much, so much going on with it. So it's really cool, and I think it's really impressive to see that. So again, if you go at high tide and low tide, that's when you're going to have the largest reversing fall effect, just because that's when the water flow is the highest. This was when the tide was going out. It's flowing out of the salt pond into the bay, and then the wave is on the other side when the tide is flowing in. So that wraps up what I had to say, but I would love to open up for questions. We have a couple minutes left. And just to say before we get started with that, if there's anything that I can't answer, or if there's something that you wanted to ask but we don't get to you since we only have 15 minutes, feel free to shoot an email to info@Blue Hill Heritage Trust. It's up here on the screen if you want to write it down or screenshot, and then I will get back to you on that at some point.
Awesome. Thank you so much, Vienna. That was a really great presentation. I think you took some pretty complicated concepts and made them very clearly explained, and it was very thoughtful, and I love the diagrams as well. So great job. So yeah, with that, we're going to go ahead and open it up to audience questions. You can use the chat, you can use the Q&A, and I will relay them to Vienna. And as she said, if we don't get to everybody, or if you think of something later, go ahead and email us. Vienna, I see one in the Q&A. How about Gulf Stream tidal power?
Yeah, so that's a cool one. The Gulf Stream is, for people, I'm sure you guys are familiar with the Gulf Stream, but that is one that's kind of further offshore. So you wouldn't really be able to apply tidal lagoon technology or the barrages to that since it is further offshore. But I do feel like there would be potential for the in-stream tidal devices. I'm not sure of the actual water speeds of the Gulf Stream. I'm sure it varies depending what area you're in. But as a rule of thumb, the areas with the most potential for that technology, the tidal current technology, is areas where the speed is 2.5 meters per second or higher. So that's why the Bay of Fundy is a really great potential site for it. So if the Gulf Stream, if those speeds are reached regularly, then I think that could be a really cool thing. You could definitely do it on a bigger scale since that is a wider ocean phenomenon. But yeah, that's a cool idea.
Awesome, thank you. While people are, pardon me, thinking about other questions, I will just go ahead and say that programs like this, and actually our internship program in general, are supported through our donors and our supporters. So if you've been a supporter of ours in the past, we thank you so, so much. If you'd like to become one in the future, please go ahead and email that address or visit our website. And I see another question. Sorry if you've already answered this, but do you know if other countries have successfully generated power from the tides?
Yeah, so there are some in Europe and then some in Asia. I know Japan and Russia both do. There were some other countries as well, but I can't remember them all off the top of my head. But I know that those ones specifically, I can tell you for certain have operating tidal barrages. I don't know the statistics of the actual output of those facilities, but I know that for sure at least those guys do, and there are a couple other ones. In Europe, I think the UK has some besides the Swansea project that are operating. The Swansea was just going to be the first tidal lagoon that actually opened, which is why I shared that one specifically by name. But there are other barrages in the UK that are operating, and like I said, I know Japan and Russia do as well. So.
Great, thank you. Is the resonance the same as with tuning forks?
Yeah, so that's actually a really cool question. The waves with water, it's hard to think of it as the same as a sound wave, but they are both types of waves. So the resonance that happens in the Gulf of Maine, it is the same concept as when you have tuning forks. If you guys aren't familiar with tuning forks, they have a set frequency, and it's cool. If you have one tuning fork and then you kind of ring it and then you set it next to a tuning fork that has the same frequency, the second tuning fork will actually start to vibrate as well and produce that sound. And that's because those sound waves are in resonance and they kind of start flowing through that tuning fork and they set it off and trigger that kind of chain reaction of motion and amplification. So yeah, it's the same concept, just a very different context.
Great. Somebody just wrote a comment. Great job. That was super fascinating. Next question. For some perspective, just how much of of the US would a 7 to 8 gigawatt tidal power supply power? Could we power everything with tides?
Yeah, so you could power a lot with tides. I don't know exactly for sure if you could say everything. There's a lot of other stuff that goes into it with just the way the power is cabled in and attached to the grid. But I can tell you the Vineyard 1 offshore wind facility that was going to have an output of 800 megawatts. That one, the number that they proposed for that was that it would be able to power 400,000 homes. So that's 800 megawatts for 400,000 homes. And then if you have 7 to 8 gigawatts, you would definitely be able to power a lot. I don't think I could say everything. And also the 7.1 estimate was the absolute maximum. And I would hesitate to say that that's a number that's actually achievable, but you definitely could make a significant contribution to the energy generation. So I think it's definitely something to look into, but I wouldn't say we're just going to cut off every other source of power generation.
Okay, how will rising ocean levels affect tides in the Gulf of Maine and the Bay of Fundy?
Yeah, that's a really good question. That's something that a lot of research is still being done into because that's kind of a new phenomenon, the idea of the rising sea level. But from what I've seen, there's a lot of literature on this. So if you see other perspectives and takes, I haven't read every single thing. I'm not an expert in the field, but from my impression, it's been that the tides will kind of get more intense just because there's more water that the tide is acting on. But then there's also all sorts of things heading into that. So I think it's kind of something where we'll see once it happens. But from what I know, the general consensus is that it's just going to kind of get more intense since you have a higher volume of water that those forces are acting on. So, but we'll see.
What part, or do you know what part of the infrastructure that actually caused the death of the whale and the fish in that example you gave earlier?
Yeah, so I don't know exactly, but my guess would be just that they went through the turbines since that's the only way to pass through the barrage. I'm assuming that's what it would be. And if you can imagine those large turbines being spun really fast by the water, if you get swept into that just along with the tide, there's nothing you can really do. I know the one whale that was just trapped on the wrong side. Obviously, that whale made it through and survived. I don't know if there were any injuries. I didn't see too much about that, but I'm assuming just the turbines is what is the main driver of mortality. And I'm fairly certain that's what the main issue with actual dams is as well. So,
Can you please explain tidal heights a little bit more? Is that simply the height difference between high and low tides?
yeah, so that's exactly what it is. It's just the tidal range. High tide is one level, and then low tide is the other level, and the difference between that is the tidal range. And I know I probably said the word height at some points, but it's all the range. So that was my bad if I mixed up those two terms a few times. But yep, the tidal range, difference between high and low tide.
Is the water flow in the Gulf of Maine influenced by the Bay of Fundy flow?
So I would say that they kind of act more as a combined system than influencing each other. Since the Bay of Fundy is directly like connected to the Gulf of Maine, it's more like water flows up into the Gulf of Maine and then naturally gets funneled into the Bay of Fundy. It's not like the Gulf of Maine itself is like pushing the water or anything. It's just the structure and the shape of the Gulf of Maine. The water kind of naturally just flows up into the Bay of Fundy. And then when the tide flows back out, it just kind of naturally flows back out into the Gulf of Maine and then out into the open ocean.
Awesome, thank you. Are there any significant regulations or other obstacles preventing the development of this area of power generation? Or is it just a relatively new field compared to traditional power sources?
Yeah, that's a really good question. Honestly, I'm not sure. The Forest Research Center and the Annapolis facility are both Canadian, so I'm not too familiar with Canadian policy regarding like ocean power and offshore power. But I'm assuming based on the fact that other countries do have operating facilities that there is a legal precedent for that and there is like a permitting process and all of that in place. I don't think, as far as I know, that the US necessarily has anything set up that could operate under besides just like the leasing process for like an offshore wind facility. I'm assuming it would be similar to that since it's also an outer continental shelf resource. I'm assuming it would be the same idea of that. You would go through Bureau of Ocean Management, but I'm not sure if there's anyone who's actually proposed a project for that. And I do think that's because the Bay of Fundy is the most ideal spot for it. The Gulf of Maine, there's definitely still potential, but the Bay of Fundy is where you can get the most bang for your buck, I guess. And that is in Canada, so that's not really in our jurisdiction. But yeah, that's an interesting one. I would have to look more into the legal framework of like the UK and the countries in Asia that have it operating to see like kind of their permitting process and how they go about actually leasing that out.
Yeah, someone else commented, that's an interesting question because it's possible that countries that abut Canada or the US might object to ocean tide disruption. Yeah, it sounds like a very controversial thing, or it could be for sure.
Yeah.
So if anyone has any other questions, we do have a few more minutes. I'm going to put in another plug. This one is for our third and final intern presentation, which will be tomorrow. Renee is going to be stationed at Petersbrook from 10 to 12. She'll have an informational table. It'll be a drop-in. So if you want to come in and chat with her for a few minutes before you go on your hike, she will be there with some members of the outreach team and other interns tomorrow from 10 to 12. If you can swing by, if you're in the area, we'd love to see you. As I said, all three interns have been amazing, and we thank you all so much for your support. So I think I've covered all the questions, but again, feel free to email us and we'll get back to you. I want to thank you again, Vienna, for that presentation. That was great. And I want to thank everyone who joined us this afternoon. Thank you so much. It's a beautiful day and you chose to spend it with us and we really appreciate it. So, oh, one other thing. Our Friends from the Field webinars will start up next month. So keep an eye out for those as well. Excellently well researched. You represented BHHT so well. Awesome comment. Thank you so much for sharing that. That's great. And you're getting a lot of hearts and clapping
Thank you guys all
emojis.
for coming.
Yeah, awesome. All right, I'm going to stop the recording and shut it down. If you want to watch us later, go ahead and look at our YouTube page. We'll have this up soon. All right, thank you. Bye, everybody.